This is Module 1, Theoretical Yield and Percent Yield with Madison Hartwick. To recap Module 1, we have reviewed concepts such as stoichiometry, and within that idea, the mole concept and balancing equations. We will go into depth of another idea within this area and explore theoretical and percent yield, as well as the idea of limiting reagents, and a quick review of dimensional analysis and the mole hub. I have chosen to do a quick review on dimensional analysis, as you can use it remotely everywhere we do math, because it simply uses the relationship of the units to convert between them, and you can also use it to check your answers. Before we use this tool, we must ask ourselves a few questions. We're going to want to ask what units are given, what are the units we need, and from there, we need to create our own common conversion factor. I will lead you through a very brief example of dimensional analysis, and from there, you can use it to check your answers all the time. So to start, we will do a conversion of units through a density calculation. So we are given density in grams per centimeters cubed, but we want to take that up 2 powers to grams per liter. First, we want to realize that 1 centimeter cubed is equal to 1 milliliter, and therefore 1,000 centimeters cubed is equal to a liter. Using this information, we create a conversion factor of 1,000 centimeters cubed per liter, multiplying this by our value in grams per centimeters cubed. The centimeters cubed will cancel out with the centimeters cubed of the conversion factor, and we will be left with 7.8 grams per liter. You have definitely all seen the hub before, as it is a very helpful tool when doing basic chemistry questions, but I wanted to do a very brief review on it to make sure everybody has access to this resource. The hub shows us relationships of equations we can use in this course and possibly others, and how the n value can take you from one equation to another. Feel free to screenshot if you haven't taken a note of this in your lectures. Now, diving into the topic of focus, we are going to talk about theoretical and actual yield. A yield of something means how much product you can create from your reactants, and ideally, we would like 100%. But in the real world, reactions are not perfect. As written on the slide, many errors can occur throughout a lab to make your yield not 100%. So the products that are produced in a reaction that has actually taken place is your actual yield. The amount produced when we run this reaction through on paper is called your theoretical yield, or in other words, the maximum amount of product that can be produced if the reaction went to plan. But to understand how to calculate theoretical yield, we must first understand the individual components of a reaction and how they contribute to yield. In order to further explore the idea of theoretical and actual yield, we must first look at the concept of limiting and excess reactants and how we use them when calculating yield. To start off, we have our reactant or reactants that will not be fully used up during the reaction. These are called our excess reactants because we begin with excess of it and we will have some left over when the reaction is completed. A limiting reactant is the reactant in the reaction that will be completely used up. We only have a limited supply of this reaction, so we must be careful when we use it and how we use it, as it will be the determining factor in how much product we can make. Thus, we focus on the limiting reactant when calculating our yield values. Now, I will take you through a problem where you find the limiting reagent and use it to find your theoretical yield. The problem we are given is a 3.6 gram sample of aluminum reacts with a 6.57 gram sample of Cl2, according to the equation below. What is the theoretical yield of aluminum chloride in this reaction? Obviously, to solve this problem, we incorporate our knowledge of limiting and excess reactants and figure out which reactant is which. To start off, we will convert the masses we are given in the problem into moles using their molar mass quantities that we receive from a periodic table. To do so, we take the mass of our reactant, multiply it by a conversion factor, which in our case will be moles per grams, as we are converting to moles. If we were converting from moles to grams, we would use a conversion factor of grams over moles. Next, we insert the known quantities, which will be 3.6 grams of aluminum for the mass of the reactant. In our conversion factor, you would want the molar mass from the periodic table to be dividing, as it has the unit of grams to cancel with the grams of the initial value. We then simply have 1 mole of aluminum on the top, as it is the equal quantity of the molar mass in grams of the moles. We repeat these steps with the second reactant. Now that we have done that, we can find our limiting reactant using mole ratios. I will only be showing one method to do this, but there are multiple methods to find a limiting reactant. The chosen method uses a mole ratio between aluminum and Cl2, so we can determine how much Cl2 we need to fully consume all the moles of aluminum, which in our case is 1.33 times 10 to the negative 1. We have the same idea with the thing we are trying to cancel on the bottom of the ratio, and this ratio is the mole coefficients of our reactants from the balanced equation. We multiply this ratio by the number of moles of aluminum we got from its mass. We will get a value that is either smaller or larger than the previous calculated mole value for Cl2. If it is smaller than our new value, which in our case it is, that reactant is the limiting reactant. If it was bigger, the other reactant would have been the limiting factor. Our final step in determining the theoretical yield of aluminum chloride is to use the number of moles of our limiting reactant, Cl2, that we calculated when converting the masses, and simply multiply it by a mole ratio of 2 moles aluminum chloride over 3 moles Cl2. Again, what we are trying to find is on the top, and what we want to cancel is on the bottom. Converting back into grams, we can multiply our last calculated value of moles of aluminum chloride and multiply it by our conversion factor of the molar mass of aluminum chloride divided by 1 mole to cancel out the mole unit. We then get 8.2397 grams, and to the correct amount of sig digs, 8.24 grams. Now that we have calculated our theoretical yield, or what theoretically should be produced, we complete the real-life experiment of our desired reaction. We weigh out the mass of the products to get our actual yield. In the next slide, we will show you how you can mathematically compare these two values. Combining all of the previous ideas, we get to the arguably most important and useful topic of percent yield. This yield entails a comparison of the two other yields to show how far off your actual yield was from your theoretical yield. To show an example of this, we will use the previous question and its values. So let's say in our real-life reaction of aluminum and Cl2, we produced an actual yield of 6.97 grams. We can use the equation for percent yield and divide our actual yield by the theoretical yield. Then we will want to multiply our result by 100% to get the desired percent unit. When we plug in our values, we receive a percent yield of 84.6%, which is reasonable and actually fairly good. Obviously, something higher is always desired, but in relation, this was a good yield. If we had something much lower, although sometimes acceptable, it may mean that you have gone wrong in your experiment and lost some of the product or reactant. If you see over 100%, then it is likely that you have an impure product and the added mass is from other compounds that were not desired. As said many times prior, real-world reactions don't always go to plan, and again, many things contribute to the loss of product and efficiency. This is extremely important in not only the pharmaceutical business as mentioned on the slide, but any other business that creates product, as any waste, inefficiency in product is a waste in their money. The process of creating drugs is already super long and difficult, as it takes years of studies and trials before it can be approved by the FDA, and then some more after that. They are already spending so much time and money on their project, they can't afford to lose any available yield, and ultimately, their money. Although chemists are most worried about the final product, they are also worried about maxing out yield along the way. Again, because it can take many, many steps to produce a final product, and if you lose some along the way, it can have great effects on the final yield. To also maximize their yield, chemists should always make sure to purify their products after the reaction, as the dilute product will give a higher false percent yield than expected. Now we have reached the end of the tutorial. Congratulations! We covered Module 1, specifically its components of yield, and now you should be able to calculate theoretical and percent yield, calculate the limiting reactant, and why yield is so important to the economy of industries, and much more. I hope you found this helpful. Until next time.